Follow Shadow Junior Twin.
Hello everybody, so today we're going over big O notation, a beautiful topic because it's so short, and to be honest, you just have to memorize some stuff. You need to know what it actually is, the different types of time complexity you could deal with, but then you just need to memorize the best, average, and worst case scenario for all the searches and sorts. That's okay, I have a table for that. We're just gonna copy that table down into our brain and we're never gonna forget it, and this topic is piss easy. So, we have 130 days until paper one, loads of time, let's get started. So what is big O notation? So it's a way to define an algorithm's scalability and efficiency, and it's in a generalized sense. But why is it generalized? Well, since we're dealing with large values of n, as n tends to infinity, we only want to care about the highest order term. If an algorithm has n squared minus n worst case comparisons to fully execute and finish, we only care about this highest order term as n grows because that's going to be contributing the most to the final result. So the big O would be O of n squared. We only care about the highest order term, and that's why it's generalized. Anyways, so I already repeated this, but we only need to know the different types of time complexities, which is on the next slide. The worst, average, and best case time complexity for the search and sorts, which is on the slide after that, and as long with the space complexity. Space complexity is quite intuitive. But anyways, let's go through the different types of big O notation. So down here we have constant. No matter how many elements are in an array, no matter how many things you're dealing with and comparing with, it will execute in an O of 1 runtime. And you could think about this being, I don't know, if you were searching for a list using a linear search, but the item you're targeting is always the first item in the list, it's going to execute instantly. So I have these written down here. So we have constant, logarithmic, which is here. So I don't know why it's the same on the graph, but logarithmic is definitely worse than constant, but it is better than all the other ones. So I've written it in their order. We have logarithmic, we have linear here, then we have polynomial up here. This is a combination of linear and logarithmic, which comes up quite a lot in terms of the searches and sorts time complexity, so that's why it's on this graph, but doesn't actually have an explicit name we have to worry about. Here we have exponential because we have n in the exponential, so we have 2 to the power of n here. And then we have factorial. Factorial is easily the worst. For example, if we considered n to be 10, 10 factorial is obviously greater than 2 to the n. 2 to the 10. And then we have 10 squared. And then we have, I don't know, 10 log n, log 10, so on and so forth. Yeah, so it all checks out, right? Anyways, that doesn't matter. This is what we need to remember. This table here. Very, very important table. And some of these are quite intuitive, some of these aren't. I would recommend just memorizing these two here. They're not really easy to just think up on the spot. The other ones you can kind of just know if you know how the sorts and searches work. But I would just recommend memorizing these two. I'd recommend memorizing everything in here. The little slip-ups can cause issues. But like, for example, if you remember that bubble sort is the same as insertion sort, then you have these two sorted out if you memorize one of them. Stuff like that. But I'd recommend just memorizing this whole table. Um, I've derived the worst case time complexity on my page if you want to see that. And then otherwise, this is everything you need to know. So what does space complexity actually mean? Because I haven't talked about this. Well, space complexity is just how much memory does the algorithm need to fully execute. Now, all of these are O of 1 because you only need to store the array. That's it. You need to loop through this array in these algorithms, in these searches, but you only need to store that array. You don't need to create more memory to execute this algorithm. That's the same for the bubble and insertion sort. And that might not sound right for the insertion sort because you're splitting it into an unsorted list and a sorted list, but you're not actually splitting this in memory. You're splitting it as you're inserting elements into the sorted list, but in terms of memory space, you're only dealing with that one array. However, with the merge sort, you're splitting your list into n elements, right? You're splitting the list down into you have elements of size 1, and you have n of those because your list is n length. And then a quicksort is O of log n because it uses recursion to split up its lists, but it doesn't split down to lists of size 1. So that's what I'm saying, just memorize these two, they're a bit fidgety. Anyways, that's it. That's all you have to know. Now there are some questions we need to go over, but they're literally, if you memorize all that stuff, you can answer any question. And I think this question here is trying to catch you out because it asks you for the worst case time complexity, space complexity, and the best case space complexity. These are both the same. For both of these searches, O of 1. And I think it's trying to see if you actually understand how space complexity works and see if you know that no matter whether you're dealing with the worst or best case, it's still constant. The space complexity doesn't change. Anyways, this question down here asks about average time complexity. And from the table, we know this is O of log n, and this is O of n. Yeah. And then here, we've already finished all the big O questions. There hasn't been many big O questions, so maybe that's going to be in our paper next year. But identify one situation where linear search is more appropriate than a binary search. Lists not sorted. A binary search relies on the list being sorted, so linear search may be more appropriate in this sense. So, O of 1, O of 1, O of log n, O of n. Data is not sorted. Now, big O does come up in long form questions, but it would be like, compare the usage of a merge sort and a bubble sort. Mention the big O of these algorithms. So although it's in the 9 or 12 marker, you're just talking about the sorts, and then you're bringing up the space and time complexities, blah, 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 which is in this table here. You just have to memorize this, and then you can apply it to different questions. You might think, oh, a binary search is better than a linear search because it's big O on average case scenario is better. O of log n is better than O of n. However, the list needs to be sorted for a binary search, so linear search might be better for small cases of n because the list needs to be sorted for a binary search. Stuff like that, you know? You just have to apply your knowledge, which is a skill we will get better at as we do more questions, but that's big O. Thank you for watching.